So 1, 2, 3. And go. So hello everybody. Right now you should probably be seeing me if everything is working fine. This is David Cuartillas, co-founder of Arduino, and I'm transmitting live from the shed in my garden, and it's going to be my secret lab. And today I have a special guest that helped me fixing everything, and he's sitting here. It's Bobby. Come say hello. Everybody, this is Bobby, my daughter, good technician. Okay, thank you very much. And so from now on, you saw that the first thing we've done is that we have changed the setup of the channels for the chat on Discord. And the reason for this is that there's been some requests that people want to make announcements, people want to ask technical questions, and so on. So there is like a couple more channels right now. My intention is really not to replicate or eliminate the Arduino forum, which is extremely useful. It's just people that have like a quick question and they don't like for example, going to IRC. You could come here and start using the channel. Okay, so today we have a lot of stuff to show. I hope I will manage to keep the program just 1 hour long. But basically there is a promise from a previous livecast of showing a specific sensor that is extremely cool, which is this one that I have in this small box here, which is Bitcraze's flow sensor. Bitcraze is a local company here in Malmo, and they developed this super nice sensor, which is a combination of time of flight and kind of like a mouse sensor with a modified optics. So it can detect X, Y, and Z. Sorry. And but the reason for me to use this sensor is actually to besides that you can use it to navigate stuff. It's very interesting because you can use it for other things, which is to detect presence. And I like these kind of sensors that you can use for multiple things and that you need to combine. When we were, for example, at BET London, which is this fair that happens at the beginning of the year, that is meant for educators. There was a company I was making a combined sensor of ultrasound and infrared to detect objects at short and long distance, because with ultrasound you can go long distance and with infrared you can go short distance. So the goal of this livecast is going to be to look at different devices to measure presence. And so I have here a lot of different things in this cardboard box that I look for in my lab. And we have first infrared sensor, a different type of infrared sensor. This one might require me to solder some wires because it doesn't have anything. The cool thing of being here is I actually do have a soldering iron, so I might go live soldering. There is a PIR from Parallax that you see here. There is some other PIRs that you can find around. I will explain which are the differences between them, how they work. And of course we have the old classic, which is the ultrasound sensor. We have the ping from Parallax. We have the HCSR04, the classic one with 4 pins, and also we have here MaxBotix, which is a very complex ultrasound sensor that can detect multiple layers of distance, has a serial port and a lot of other things. So I don't have time to go through the whole thing, so I'm gonna start a bit with, I'm gonna be very quick, because I would like to also use this video as a reference, and later on, if there is more questions, we can of course look at making other things. So we're going to start by testing this, which is LDR, a light dependent resistor. And you will say, why? Well, many times people want to make a project when they want to detect that somebody is touching something, and they want to use infrared, ultrasound, whatever, complex and cumbersome and expensive stuff. And sometimes this very cheap and very tiny can be solving the issue. And as typically happens, I took this from a box somewhere and I have no idea which is its value. And the property of an LDR is that it's going to be changing its resistance value depending on the amount of light sitting on it. And it has a maximum resistance that could be between 2 and 5K or 10K. And this one in particular, I don't know how much it is. And intentionally, I didn't bring the multimeter, so I'm just going to show you how I would do it if I didn't have a multimeter. And I will typically take some resistors, and here I have with me, I took 3 resistors. One is 1K, one is 10K, and the other one is 100K to make a voltage divider with a slide resistor and check out which is the one that gives me the best range. The idea is going to be to then to start first with this one, with the LDR, then jump to the classic ultrasound because it gives distance. We might skip the traditional sharp infrared sensor, mostly because it's exactly the same thing as the ultrasound and it will be just repetition. Just I will just talk about how it works, but I will probably not mount the circuit because there will be no time. Because I would like to try the PIR, which is passive infrared, which is a different technique that is just meant to detect movement. And I will just talk briefly about it. And then the star of the night, which is the flow sensor. Hopefully we will just make it by then without really be starving, because here in Sweden it's actually dinner time already now. So let's get started real quick. So I'm going to show you one of my tricks that I use at the university many times, which is like if I want to not lose the boards from the breadboards, I glue the boards to the breadboards, like in this case. It's done with a bit of double-sided tape. So for a lot of projects, it gets very practical. So I can very quickly mount stuff. And I'm also going to show you some of the nice things we've been preparing for today. Like we have a lot of different cameras. Like I have this one, and I have this one, and I even have one with multiple cameras, desktop and everything. So I'm learning slowly how to use the LiveCast so we can get better transmissions. So we're going to take a look at this particular experiment right now, which is the one where I'm talking, but I realize now I'm just changing windows by myself, but not showing you the actual windows. So this is now the window. So I'm gonna be showing you the first experiment with the LDR and the Arduino board. And the basic principle for this, if you're unused to it or you have never seen it, is that you will put an LDR, which is the light dependent resistor, and you will put a normal resistor, and this is the one which value I want to be changing just to make sure I get the best range. You put 5 volts in one, 0 volts at the other side, and this will be the sensor input that will go to an analog pin, for example A0 on Arduino, and then I will just read this value on the serial port and see the result. So when there is more light coming here, this will change the properties of this material, will change the conductivity, and it will change the amount of current and how the voltage is divided here, and therefore the light will basically change the amount of voltage coming to Arduino, and in that way behave differently. So the way this is mounted is very simple. I will make it exactly as I did on the drawing. First the LDR. I'm going to choose my 1 kilo ohm resistor first, and I will mount it here. We don't have really great light in this room just yet. We just moved in, so we need to work a bit with improving the light qualities. Here you go. So then we just take 3 wires. So these ones are nice because it's red, black, and orange, so you can have different colors. And I'll put brown for ground, red for power, just to keep some consistency. There you go. And orange for the signal, which is going to be the pin where both go together. I want to take this for a second because this is a transparent breadboard and it's not like I can see perfectly. There you go. And this go to Arduino. Brown is for power, for ground, sorry. Red is for power, 5 volts, and orange is for A0. And I have to say, I took this from a box just before coming here. I have no idea whether it actually works. So the risk that this will explode in my face is fairly high. So let's just connect. Let's just connect this guy here to the USB port. There you go. It seems like the board at least is going on. And you can't hear the notifications, but they are buzzing extremely loud in my headphones. And I will just change window to show you the this one here. No, so the Arduino one, sorry. I remind you what we have is an LDR connected on A0. So this could actually be done with a very classic example, which is analog in, serial out, but I'm going to write it from scratch real quick. So I will just start a serial port, serial begin, 9600, and here I will just read into a variable. Well, I don't know how this is behaving for you. I realize now. You're seeing, yeah, because you see that the thing is flashing quickly. It's because there is some weird configuration in my computer. I can't change it right now because we're live, so you have to live with that. But basically, what's happening is that if I press some numbers, they automatically change the scene. So, and I'm programming, so I'm going to be pressing numbers a little bit. Anyway, so I'm going to make sure you can see the code. This is the code, and there you go. There is the code, and now we continue to program. And as I said, I read the signal from the analog pin, analog read A0, and I send it through a serial port, serial.println the value. I will make a delay here of like, I don't know, 400 milliseconds, completely random number, so it works. I choose the serial port for the board. It's connected to COM port number 5. I upload to the board, and there it is compiling. And once it's done, it will start sending stuff. And I'm gonna open the serial port monitor to just check, and I will just change window here so you can see the serial port monitor, you can see the board at the same time, and you can see me. And in this way, now we can check that the thing is working. I will cast a bigger shadow on the sensor, and you'll see how the value, oops, oh yeah, and you see it again. When I cast the shadow, you see how the number goes low, and when I take it out, it goes higher. And if I cast a bigger light on it, I'm going to just turn on my mobile phone. I'm going to turn on the flashlight, and just check on this flashlight. So I will project more light on the sensor, and you see how it even goes up even higher, up to like 450, 460. So you see, it is very simple, because now if I want to detect that somebody's coming by, I can just detect that somebody's casting a shadow, and there is a change, and you can imagine how easy it is in the code, or the code that you need to produce to just detect this shadow and change something. So it's pretty straightforward, kind of easy to do. And I realized, okay, if 1K resistor is enough, I don't need to go changing with the other resistors. This means it's probably a 2K as a maximum value resistance sensor, which means that at its maximum value it gives me 2K, and that's kind of like the bridge I'm making, voltage divider I'm making with the resistor, and that's why it gives me the value it gives me. So this works great. You can use this for many things. If you have 2 sensors instead of 1, you could be detecting, for example, a direction of movement, right? Because you could detect that the shadow is being casted first in one sensor and then in another sensor, and that's super inexpensive and can be used to produce magic in installations. I brought with me a laser, actually, because this is how many students that in the place I'm showing are making their own harps. They use a laser like this one, and they cast a laser light on top of the LDR, and in that way they have a stronger light that works when you are in a live environment with a lot of people. And the question is whether this laser will work. I have no idea, again, because I took it from a a box in the lab and probably has been used for other things. So I'm gonna try to punch it using a small trick. I will just punch together a pin with the actual connector on the board and see if I can just get it to work. So I'm going to first plug in ground, and then I will plug in 3.3 volts. Because these lasers, they either work at 3.3 volts or exactly at 5. And if they work at 5, I have to make some more work. And so this might not work. By the way, I didn't have the time to test it before I came. No, it's not working. Okay, so I will not pursue this because it will take me some time, but you get the idea basically. If you have lasers pointing at LDRs, you can just change the kind of shadow you're casting on them and detect how it's working and so on. So it's pretty easy to build. Okay, so let's check out the next sensor. Anyway, I will first check whether there is any questions in the chat. I will every now and then be coming back to the chat on the LiveCast channel to check if there's any questions. So please feel free to ask any questions you have, any comments on whether things work or not work for you. We can answer live. Also, there's a couple of very notable people in the audience here, so it should be very easy to get questions answered live. Okay, so we continue. And we're gonna go to our next sensor. We'll just disconnect one I have here. Our next sensor is gonna be, as I anticipated earlier, the ultrasound. And the ultrasound is a traditional sensor, and many people use it. You can find it for very cheap. I do have an original from Parallax here, so you can see that. It may be hard to read because the camera isn't focusing, but it's an original pink sensor from Parallax that has 3 pins. Then I have one with 4 pins, the HESR04. The difference between these two is actually you can use them in different ways. You can use the HC just as a receiver and not use the emitting part, so you can have a transmitter on one side and a receiver on the other. Those are interesting differences. And then we have the one from MaxBotix, which is a lot more expensive, a lot better. So I'm gonna just make some drawings explaining how they work, and then I will take one of them and you can infer a bit how the other ones work. Okay, so I will just first pass to the next page in the notebook. And get the top camera. There you go. Center it a little bit just for the sake of clarity. And let's see how this works. So first of all, we have the 3 sensors here. And first you need to know some basics of ultrasound in case you don't know, and I will just say these ones. If you already know, please bear with me because the fun part comes later. So typically ultrasound works through the emission of a tone. So this is a tone, but it's at a frequency that the human ear theoretically can hear. So this is a person, and this is actually silent for us. We don't hear it. It's over typically 38 kilohertz or more. 38, 40, 60 kilohertz, whatever. And the idea is that these transceivers, what they do is that they optimize when they get a train of pulses in a certain frequency, which is oscillated at a certain frequency, they translate this to the air. So they get a digital signal and they oscillate, and then they send this through the air. This signal travels through the air, bounces on whatever object, and then travels back. And then there is a second transceiver, as you see there is 2, that takes this one and translates the answer into a pulse that tells us for how long the signal was flying. I'm going to take a pen just to signalize one thing. I'll take a different color, because while the signal that we transmit is a burst. We typically call it a burst of a certain quality. After the signal has been traveling through the air, bouncing on something and coming back, the signal gets really distorted. So what we see is more or less like this. So we need some processing power on this side to translate this into something we can work with. So the signal is what Arduino needs to get through the transceiver. The signal is what we get from the transceiver. And the signal is actually made in a way that translates the distance into a pulse of a certain width. And this width is computed in terms of the flying time of the signal. Because we know the sound goes typically at 340 meters per second. From the moment we send this until the moment we get the echo, some time will pass, and that time that passes is translated into a pulse of a certain width. So this is the way we measure how long it takes for a signal to fly. That is translated into the pulse, and the pulse is basically telling us the distance to an object. If you know the time, we multiply by the speed. Then ultrasound is extremely sensitive to different conditions. Ultrasound is very sensitive to, for example, humidity. So right now in our shed here is pretty humid and it's raining outside. So probably the quality of the measuring should be handled with a different kind of formula than the one that comes by default. But this is not like a scientific measurement, so it's just for checking the distance to objects, so we will live with that. Okay, but you should keep this in mind. So the way you connect this again goes through taking your board. I will dismount the previous circuit that was pretty simple to build, and I'm going to start using the ping sensor because it has 3 pins. And what happens with the ping sensor is that it has a 0 volts pin, a 5 volts pin, and a signal pin. And the signal pin is used first as a way to transmit the burst. It sends a signal that says, okay, get started. And it's then transformed into an output pin so that it can talk to Arduino and tell Arduino the pulse in a certain way. And this is something that many people don't know, but in Arduino you can actually write your program so that a pin is first an input and then an output. It's perfectly possible. So let's just connect the pins here. So first is ground, then is power, and then is ground, then is power, and then is signal. Okay, we just make sure. So, and then I plug it to Arduino, ground, 5 volts. And then the signal is actually a digital signal, and this is very important. People don't understand this, but we are not dealing here with an analog signal, not with a ping sensor. We're dealing with a digital signal. And what I'm going to do is that I'm going to look for the software to this sensor. The Arduino IDE does have some software, but it's not necessarily for this sensor. So let's take a look at the IDE first. And here we go. I will just open the examples, and there is sensors, and you have here ADXL, which is an accelerometer, NOx sensor, MEMSIC, and ping. Okay, let's open ping. And let's see what ping has to offer. I will just put the code here. So this is the ping sensor, and let's take a look at the code. So the sketch first has some comments where it explains how you should connect everything, and it tells you I should connect the signal pin to pin number 7, which is exactly what I did. It was a bit by accident, but it's really good. And then it continues, and it configures a variable, well, a constant ping pin, which is the pin where we'll connect the pin. It starts a serial port with serial begin. Then it declares 3 variables directly inside the loop. One is duration, inches, and centimeters. So duration is going to measure the time of flight that I told you. Then the inches is going to give you the distance in inches, and the centimeters is going to give you a distance in centimeters. So the first thing that it does is that tells the ping to become an output. Makes it an output, it sends out a pulse. So it makes the ping go low for a couple of microseconds, sorry, then it goes high, and then it goes low again. So it sends a pulse like check. And that tells the transceiver, send out the burst. Sends out the burst, flies through the air, comes back, and then we measure it. So in order to measure it, the next thing we need to do is to transform the pin into a digital input. So here you have the ping that was an output until now, and in the middle of the loop we transform it into an input. So this is perfectly possible to transform an output pin into an input pin. And we call the function pulse in. And pulse in will detect for how long a pulse is high. This is a standard function that you can use in your programs, because there is actually a lot of these sensors out there, especially older sensors, that give you measurings in the width of a pulse. And you get the duration, and then you can convert the duration through mathematical operations. And these mathematical operations are functions that are farther down in the code that we will explore. We say take the duration and transform it in inches, take the duration and transform it in centimeters, and then print out the inches and print out the centimeters. Let's take a look at the conversion function, and it is pretty straightforward. For example, the 1 to centimeters, it tells you here that the speed of sound is 340 meters per second, or 29 microseconds per centimeter. So if you know how wide this pulse is in microseconds, you can automatically extract which is the distance in centimeters. And then you need to remember that the signal is going, bouncing, and coming back. So you need to divide it by 2. So it's not enough to just divide it by 29. You need to divide it again by 2. So if this was a much more scientific device, then we should take into account humidity in the air, for example, the speed of the wind, and other things that we are not taking into account. This is good enough just for measuring very easily distance, as you see here. So let's put this on the board, just like this. And I'm going to change view here. And once the program is running, I just need to open the serial port. And you see that now the serial port is giving us the distance in centimeters and in inches out there. And if I go closer, the distance becomes smaller. And when I go further, the distance becomes bigger. I will put at the ceiling, and now the distance will be even larger. So it's 1 meter 20 centimeters to the ceiling here, and now there's the wall. So what happens with ultrasound is that it's extremely useful technology for measuring up to 10 meters. So it doesn't really work if what you want to do is to measure very precisely between 1 centimeter and 2 centimeters. It works really well from like 5, 6 centimeters and all the way up to 10 meters. It depends on the sensor. These cheaper sensors, they give you measurements up to like 3, 4 meters. If you want to get better measurements, you should work with things like the MaxBotix sensor. That's going to give you a much better response. And one of the differences with this MaxBotix sensor, I'm going to show you the pinout. It has a lot of pins in the back. And I will just draw the pinout of this one because MaxBotix is actually a bit different in a sense that it's meant to be used in a bit more scientific operations. So it has the following pins. It has ground, it has 5 volts, it has TX, RX, analog, something that is called here PW, which means pulse width, and then yet another one that at this point hasn't been used. So basically, this is what we're measuring right now, pulse width. Analog gives you a voltage between 0 and 5 volts for the distance. So it would be the same thing as we were measuring before with the LDR. You could just very easily transform a distance measurement to something else. And then you could also read it through serial port and give commands to it. like you could make it behave in certain ways, which is very interesting because it's very different from other sensors. There is different types of MaxBotix sensors. Some of them they can pile up to 7 or 8 measurements, so they can receive. They don't listen just to the first echo and stop. They listen to multiple echoes. So in that way, they can give you the response of multiple objects on the way. And if you, in case you don't know how the coverage works for something like a sensor like this, you should just think about it that if you have a sensor here, the coverage for the sensor is a beam that is more or less this shape. So if there is multiple objects on the way, all of them will produce an echo. And it's interesting because MaxBotix actually allows you to detect multiple objects in the beam. To be honest, I have never had a chance to try out that exact functionality, but according to the datasheet, it should be possible. So the other question is, what is the difference between the ping sensor that we have there and the HC-SR04 that we have here that has 4 pins? Well, the big difference is that the ping sensor has 3 pins. Ping sensor has 3 pins, which is 5 volts, ground, and signal. But the HC-SR04 has 5 volts, ground, trigger, and echo. This means that it has a pin for this trigger and a pin for that echo. So it separates both, and that is actually an advantage in a way. It's harder to program. You need to use 2 pins instead of 1, but at the same time, what happens is that if you had, for example, an array of these sensors, you could use as the receiving part to distinguish whether something is oriented in one direction or the other by just having one of the sensors transmitting and all of the other ones receiving. Since you know the distance between the sensors and so on, you could make the math to detect whether it's pointing that direction or that direction versus a wall, for example. So this is a bit more versatile. You can do more things with it. At the same time, if you want to just use this sensor as a ping sensor, the only thing you need to do is to solder together, as you can see in here, the trigger and the echo pins and use the exact same code that you were using with the ping. So there is always tricks on things you can do, and these are just a couple of nice tips on things you could eventually try out with ultrasound sensors. So let's go for the next sensor, and let me just clean up my table a little bit as I'm talking. So as I told you, I've been actually quite obsessed between air quotes for a while, or I was not any longer, with this particular topic, which is presence detection. And how do you detect presence, and what does it mean to detect presence? And because it's really a language matter. As humans, we talk about presence because there is someone in the room, like Bob is here. You might hear her. Because you are humans, you have developed certain abilities that can tell you that there is somebody here because you hear a noise that is not produced by me, right? So it is that simple. If you wanted a computer to do that, you need to develop or translate that ability that you know you have into an ability the computer could have, so that you can get the computer, for example, to listen to the room and understand that there is more than one person in the room. A different thing you could do is to use a camera. A different thing you could do is use different types of sensors and so on and so forth. So it depends on the granularity you're interested in. You might need one sensor or another. Like if you want really high precision and distance, for example, you will not use ultrasound sensors like these ones. You will use infrared sensors like that one because they're going to give you a much higher precision. But if you just want to know whether there is anybody in the room, then you will use something like a PIR sensor, which is the next one I will talk about. Then the rest is software, and it's on your side. It's your responsibility to write the software that will do the thing you want to. So let's take a look at how a PIR sensor looks like inside. A PIR sensor is basically made of literally a passive infrared sensor. That is exactly that thing there. It's a silicon that reacts to light and a lens, and this is a lens made of plastic, and it's made of plastic that is cut in different directions, and in that way will be able of capturing light coming from different directions. So what this sensor does, and let me just change to the top camera so I can just make the classic drawing and explain you a little bit how it works, is that it has this sensor, and this sensor can detect light, but in order to maximize the directions that this sensor can work with, we have a series of lenses that are arranged here. It's like an old lighthouse, but made very tiny around it. So in this way, if the light comes this direction, it touches on the plastic and it's redirected that direction. So you get the idea. And so that makes it very, very useful, because if you, for example, wanted to make a sensor that instead of detecting omnidirectionally 180 degrees and 360 degrees around it, what you could do, if you always wanted to like detect something that just detects like a line, you could just cover your cap of the sensor with tape or paint it black, so that it will only show an area of a certain width, and it will only cover that area, but it will not cover the full extent of the sensor, which is more like this. So this is a very interesting feature. So when you see security sensors at places, this is basically what they have. They have a system that detects infrared light, and what this thing does is that it triggers a pin when there is a change in the infrared light. So I'm going to use the Parallax sensor that I don't know where I put it, out here, just because it's easier to use. And I'm going to explain this thing I'm saying right now because it might take you by surprise. But of course, these sensors that you can buy very cheaply around, they sometimes work with an open collector and they sometimes don't. If they work with an open collector, this means that you still need to have like a resistor or something to mount this thing, and it's very confusing because you never know if it's a pull-up resistor, a pull-down resistor. If it's an open collector, it's typically a pull-up resistor, but you never know. But here we have this ping sensor, this Parallax PIR sensor that just gives you a straight output that you can use. So I'm gonna just make my circuit with this, and the important thing is this is like a button. Basically, it's not giving you a signal or it's giving you a signal. It is really that simple. And it's funny because it's not standard. Like the pinout for the sensor is the exact opposite as the one for the previous sensor that was also from Parallax. So first is output, second is voltage, and the last one is ground. Yeah, like this. So I will plug it in, and the first thing you're gonna see is that it turns on some lights there, so you see it's working. And right now I put it pointing upwards, so it will detect movement in all directions. And I'm going to make a new program. So I will just start the program from scratch. Oh yeah, I forgot. This is a different kind of keyboard, so I need to, in order to have all of the features. And the thing I'm going to do is then to register how I read a button, and the button is going to be just sending a signal over the serial port. So here you go, and I declare it's going to be on pin number 7, so I have to declare pin number 7 as an input. And here I'm going to declare a variable that will just do a digital read of pin number 7, and this will store the value from the sensor. And what I can do now is, if value is high, then serial print movement. Okay, and otherwise I will not print anything. So now everybody in this room, and that goes for my guest, has to be very quiet and not move at all once the program is running. Oh, sorry, I'm just talking and I'm not showing you the code. That's my bad. I forgot to change to show you this one. I was typing the code and I just didn't realize I wasn't on the right window. In the meanwhile, there is a question on whether we can measure water flow rate via ultrasound. You can use ultrasound for a lot of stuff. For measuring the distance of the amount of water in a pipe, you could do it. So if you make a mechanical system where you can have different heights of water based on the amount of flow over stream, then you could definitely measure water flow rate by making a translation of that. Okay, so sorry, the program is running now, so let's just change view, and in this view I need to just open the serial port. Here you go. And right now, you see, it was not detecting anything until we moved. And then once we moved, now it stopped. And if we move again, it prints again. So it's very simple to use. This is a classic alarm situation. The difference between the Parallax one and the other one that I have here, as I said, is that the Parallax one is ready to use. And this one might or might not require you to include a pull-up resistor. Also, the difference is that since this one doesn't have a pull-up resistor, because it's an open collector, you could use it to directly trigger a light, while the Parallax one will require to connect to something else to trigger the light, most likely. Okay, so this is a very simple example. So now we saw ultrasound, we saw infrared, and we saw normal light. And we're coming to the start of the evening, which is the, if I know where I put it, which is this one, which is the flow sensor from Bitcraze. And Bitcraze is a fantastic company here in Malmo. It's a small company where 4 people are working, and I really would like to show you their website so you can see the stuff that they are doing. So let me just open a browser here, and let's just Google Bitcraze. And Bitcraze.io is the name of the company. And they really are focused, or they started being very focused on flying vehicles. So their first goal was, let's make drones, and they make an open source, fairly inexpensive, fully reprogrammable drone. And you can take a look at that in products, and they have like a lot of stuff that is actually stuff that is related to the drones. Like the Crazy Fly is a drone. You have the Crazy Radio. You have LEDs to add to your drone, so when it flies it will leave light traces, and so on and so forth. Then they have a very interesting thing, which is the local positioning system, which is an ultra wideband based indoor location system. So you can use it, for example, to locate your flying drones inside a room. That's amazing, because the drones weigh 140 grams and they're tiny, like they fit in your hand. And today we're going to talk about the flow deck, which the flow breakout. The flow deck is a part that is a deck board that you add to the Crazy Fly, but the flow breakout is a sensor board that you can see here in the picture that can be used to detect movements in X, Y, and Z. And that's what we're gonna check. And they made a great tutorial in Hackster where they're showing how the sensor works. And they made it for Arduino Leonardo, and they did it for a reason, because Arduino Leonardo can work as a computer or a mouse. So when you use it, you can make it work like a computer or a mouse. And I'm not really sure I brought with me an Arduino Leonardo. I'm pretty sure I have, because I have 250 Arduino boards, but I want to do it for Arduino Uno. So I'm going to make it work on the Uno I have here. Okay, so that's going to be my goal for the day. So the sensor has a lot of pins because it's bringing together 2 different sensors, and it's using both SPI and I2C at the same time. So you need to wire a lot of things for it to work. And there's a tutorial, as I said. They have made this very nice project tutorial that is on Hackster. So let's just, I will open it. Okay, I have this computer protection that doesn't let me. So I'm gonna just hackster.io, and once here, we're gonna just look for Bitcraze, and once on Bitcraze, there's different projects. Marcus Eliasson, for example, was at Bitcraze as the CEO. And here we have the touchless mouse, and this is the one that explains how you can make a touchless mouse using the Arduino Leonardo. I'm not gonna use the Arduino Leonardo, I'm gonna use the Arduino Uno. As I said, I will just display the information on the screen. And the important thing is that you need to install a couple of libraries for this to work. On the one hand, you need to install the BL53L0X library for the range scene sensor, which is the distance sensor, if I'm not mistaken. And then for the optical flow sensor that will give you the XY coordinates, you need to install their own Bitcraze library. And so first thing is to mount it, and this is for the Arduino Leonardo, where you have the pinout. And as you see here, they take the I2C from the last pins on the board, which my board has up here, and then they take the SPI from the connector here. The thing with Arduino is that for Arduino Uno is that connector there is also replicated on the pins 9, 10, 11. So I could do that as well. So, but I think I brought a whole lot of cables. I can do exactly, just to be safe, I can do the exact same connection as you see in this drawing. So what I'm going to do is to just punch the sensor on my breadboard, and the first thing that you have to take into account that the drawing of the sensor is upside down. So like the drawing of the sensor is looking at the board from this direction. While when you're going to plug it, so this means that when you're going to plug it, all of the cables are going to be in the other direction. So that's kind of important. Okay. So before I continue to plug anything, what I will start with is by connecting installing all of the software that is needed for the sensor to work. And you need two different libraries for Arduino. So I go to the Arduino IDE, and I just make sure I have the names of the libraries. As you know, to install new libraries, you have to go to the library manager, which is inside the sketch menu, and you can just call here to VL53L0X by Adafruit, so that you have it. The one from Adafruit will work. Install it. And the other one we need to install is the Bitcraze. So I will just type here Bitcraze, and it shows up optical flow sensor, access to XY motion count, install, and close. So the moment I have installed these ones, there is actually examples that I could open. So I could go to examples, and if I look at the examples of the library, you see there is a Adafruit library down here, and it has a couple of examples, and there's the Bitcraze flow example here, which is much more complete. And this flow example is going to be reading delta X and delta Y and sending the information, so we can check that it works. So as I said, here now there is two sensors, one that detects XY and one that detects distance. This example is just to check how the XY part works. And the important part is to start by connecting everything the right way. So the problem is that my example here now is made for Arduino Leonardo, and I need to connect this thing on the Arduino Uno. So the easy way is to just follow the drawing as it is made there, just to be safe. The other thing I could do is to look for the pinout of the Arduino Uno and then make sure I connect things in the right way. So I'm gonna do the second one just because I would like to make it right. So I will just go here and I will just Google pinout Arduino Uno. And here we have multiple pictures of Arduino boards. And here is one. This is big enough so I can show you. Yes. So I will just open the image in a new window. Here you have it. So here you can see the pinout of the board. And as I said, on the Arduino Uno, the SPI is also on the pins up here. And for those of you that are not familiar with this, on top of the Arduino Uno, or inside the Arduino Uno, inside the chip, the ATmega328, there is different peripherals. One is doing an SPI connection, which is like a serial port, but can reach faster speeds. And this is the one that is connected to these pins and is used for reprogramming the board. And then there's an I2C that allows you to connect multiple devices hanging from the same line, which is connected on the extra pins that are on top here. I will just mark it with my mouse. These two pins, you see SCL and SDA. Okay, so I will just start by using a lot of wires, because I'm going to need a lot of wires, and plugging things in. So first thing, remember the top here, because it's inverted, is the ground. So I go here and I go to the other website. Here on this website I can see the connections, and since you guys don't have, I will just plug it like this because you guys don't have the sensor with you. So if you had the sensor with you, but you could always take a look at the final image. Okay, so the first one is ground. I'm going to put the brown color for ground just to be very, very safe. And the second one is power, so I'm going to put the second one red to again be very, very safe and not make any mistakes. And the next one is called CS, which means chip select. So ground is going to go to 0 volts. There you go. 5 volts is going to go to the red one. Then chip select is going to be pin number 10. So there you go, pin number 10. Okay. These are the first connections. Then I take some more wires. I want to avoid the black color just to not have any conflicts. And on the other side of the board, so if I continue, basically, I have one that is called MISO. And for MISO, I'm going to take yellow. Then one that is called CLK, which means clock. I will take green. And the next one is called MOSI. And for that one, I will take blue. And now I need to make sure that these pins are properly addressed on the Uno. And on the Uno, you see that clock is actually pin number 13. And I said that green is actually clock. There you go, pin number 13. And then MISO and MOSI are 12 and 11. And it's very easy to make a mistake here because you never know whether MISO and MOSI on the sensor are supposed to be the same ones as on the board or the other way around. And the worst thing that could happen is that it doesn't work. So I will just connect them, and if it's wrong, I just have to switch them. So pin number 12 is MISO in Arduino, and according to this, the blue one is MISO. So pin number 12 is MISO, which means that pin number 11 is MOSI. So I just plug them like this. So this is just for the XY detection. I will just try this one out, just to make sure that the connection is working fine. I will back to the Arduino flow example, and I just need to upload this one to the board and open the serial port to see if it detects my movements of my hand on top of the sensor in these directions. Right now it's compiling, it's going to be uploading in a second, and then we can check. Okay, there you go, it's working. I open the serial port, and it failed. So if it failed, it basically means that either the sensor is broken, which I hopefully think is not broken because I only have this one, or I just connected the cables wrong. As I said, it's really hard to know whether MISO and MOSI are in one direction or the other. It's always like this when you get this kind of sensors, that you don't know if they are labeled from the sensor point of view or from the board point of view. So I just plug it again. I don't need to re-upload the program because it's already there. I just need to open, and it failed initializing the sensor once more. So then I need to check whether I plug everything accordingly, because this thing should be working. Okay, yeah, I just hadn't punch the sensor strong enough on the board. So now there is no movement, and if I move my hand on top, you see how it detects the movements in X and Y. This is actually pretty amazing. So I'm going to ask Bobby to put her hand, because she's been patiently waiting here. Just put your hand on top of the sensor. So you see, it detects whether you move. This is the delta of the movement. And it tells you how many units of distance you've moved, X, Y, back and forth. So it's really, really amazing. It's super precise. It's basically when you have on a computer mouse, you see, and it keeps on running. So this is just one of the sensors. And in order to keep the speed high, this one hangs on the SPI. And then the guys from Bitcraze, they had the idea of putting the other sensor on the I2C. So let's just take a look at the drawing again. And we just add 2 more wires, and we can check the distance sensor, which is the other one. So I take 2 more wires, and I have here gray and white. So the last one on the board on the sensor is white, and the next one is gray. Okay. So the last one, SDA, goes to SDA, which is this one, and the other one goes to this one. So now remember, I'm going to be able of making a distance checking with the sensor. I will just open the example that comes in the example list from for the Adafruit sensor. So for the BL500 and 53L0, and let's take a quick look at this code. So this one uses a serial port at an entirely different speed. I'm going to slow this down, mostly because what I want to do then is to mix both programs. So we just put it at the same speed as the other one. While there is no serial port, this is a trick, by the way. If you have never seen this, you could use it. If you want to have a system that only works when it's connected to the computer and otherwise doesn't do anything, you could just add this to your setup. So the program will wait until it's connected. Then it prints some information. It tells you if it failed to boot. And it calls this logs begin. Logs is the distance sensing object that was declared up here from the class Adafruit BL53L0X. And when it calls begin, if it fails, it gives you a failed message, and it keeps on being there until it works. Sorry, it breaks, because while one basically breaks here and it doesn't continue. So I said it wrong. If it works, it just gives you the distance in millimeters. So this is what is called a time of flight sensor. It's the same thing as the ultrasound, but using different technology. So we just run this, and if it works nice, we will see how when we move our hands up and down on the sensor, it will be ranging the distance to the hand. And then we can mix both codes together and have an XYZ sensor. And that's what you can see in the example from Bitcraze and Hackster, because what they do in the example is detect that you're moving your mouse XY and then pressing a button, touching on the air. Okay, so once it's uploaded, which is now, I can open the serial port monitor, and it's saying it's out of range. And here you see the distance is super precise. I'm going to ask my volunteer again, so please volunteer, use your hand. You see how it works perfectly. So this is very nice. Everything worked today. I'm actually very, very happy. You know, when we make this live cast, things might not work, and we have to learn to accept that. And so we've seen different sensors. This one was requested by you guys since a while ago. I'm really happy I could find it in the lab and we could bring it to you so you could see it. We've seen what could be a very good pedagogical way of teaching students about how to use sensors. You could start by detecting presence by casting a shadow, and that's what you do with the LDR. It's super inexpensive, it works out of the box. The only problem is you need to have light in the room so you can detect the shadow. If it's dark, it doesn't work. If you need like detecting distance at kind of a longer distance, like 7 meters or something, ultrasound is your friend. There's different types of ultrasounds that can cover all of that distance. If then you need to detect like presence from somebody that is that needs to be very precise and in short distance, you can use infrared. There is infrared that work with different lenses. I didn't explain this. This is for enough material for a whole 1 hour program. But infrareds, there is some of them that go into between 2 and 10 centimeters, and ones that go between 10 and 80 centimeters. depending on the lenses they have. So so you could use that for higher precision. But if you're ready to spend a bit more money and you need like super precision and direction measurement, direction of the movement and so on, then you have something like the flow sensor from Bitcraze, which is fantastic to try things out. So and finally, yeah, I almost forgot. If you just want to be like in a large room, like fairly large room, and just want to detect whether anybody is moving in the room, then passive infrared is your friend. So these are the different levels of sensing presence that you can do using light or ultrasound at this point. Okay, so if you have any questions, it's maybe time to ask them on the chat. Otherwise, I think we'll just call for a day. Okay. Oh, there is somebody was asking questions, tech questions. Okay, but it's not ready to the program. So guys, you have like, I will count to 3. So if there's any questions, this is your chance. And if there is no questions, we will just say goodbye and see you on the internet. 1, 2, and 3. So thank you very much. Thank you everybody. This was David Quartiers transmitting livecast number 9 for Arduino, live from my shed with my fantastic helper today, Bobby Quartier-Stever, that was here helping out, moving a hand and making some noises in the background, and by the way, making a fantastic cup of tea. So thank you very much and see you on the Arduino Livecast. And don't forget to subscribe to our Livecast series that will be coming hopefully every week, Thursday, 7 p.m. CST. Goodbye and see you soon.